In this project, we will numerically validate the data obtained by the paper named Effects of Curvature Radius on Separation Behaviors of the Hydrocyclone with a Tangent Circle Inlet. As you can see in this slide, we have extracted the figure 1 of the paper, which shows the parameters and domain mesh of the hydrocyclone. Now in this project, based on the information provided by the paper, two-phase flow of water and air inside a hydrocyclone is simulated. Now in this slide, you can see that we have extracted the figure 4 of the paper, which shows the axial velocity over the radial position of a line.
By clicking on the subscribe button, you will be informed about the newest CFD training videos by MR-CFD. Or if you are watching the training video, click on the MR-CFD logo and subscribe.
This is the geometry of this model, which consists of a water inlet and two pressure outlets. This geometry is designed in ANSYS Design Modeler software. In this slide, you can see the mesh performed for this geometry. The geometry is meshed in ANSYS meshing software, and the mesh type used for this geometry is unstructured. By clicking on Display button, a new window will appear, which you can see different parts of your geometry. Under the Phase Interaction tab, you can see that under the Global options, we have enabled the Surface Tension Force Modeling, and we have selected the Continuum Surface Force Model. After that, under the Force Setup, you can see that we have selected a constant value for Surface Tension Coefficient between two phases of water and air, as you can see in this window. After that, under the Adhesion option, we have enabled the Wall Adhesion, and that after enabling this option, we can change the settings in the boundary condition related to the hydrocyclone wall in reference to the wettability of that surface. Now after clicking on the inlet boundary, which is a velocity inlet boundary, and then by clicking on Edit button in the appeared window, you can see that in front of the velocity magnitude section, we have added the velocity magnitude of 6 meters per second based on the paper. Also, in order to define that we only want water flow to enter this boundary, under the phases section, we select air and set the volume fraction of air to 0. After double clicking on the method, you will see that a new window will appear showing you the pressure velocity coupling. Also, you can see that the spatial discretization methods are shown in this window. Also, you can change this discretization into other formats, like you can change them into first order event and the other options available for each variable under their combo list. And for the simple pressure velocity coupling, the simple algorithm is kind of an iterative solver which uses a relationship between velocity and pressure corrections to enforce mass conservation and to obtain the pressure field. Now, as was mentioned in previous slide about defining a mass flow rate report and an arbitrary boundary, you can see that we have defined two reports in order to report the mass flow rate for two boundaries of overflow and outflow. After double clicking on the Run Calculations button in the appeared section under the Parameters part, you can see that we have defined the number of time steps and each time step size. Also, you can see that we have maximum of 20 iterations per time step. After defining these values, we click on Calculate button so that the software will start the simulation process. Now after defining a plane, we go over the contours and right click on it and then select New. Now in this slide, you can see the contours of volume fraction of air, and you can compare this contour with the contour presented in the paper. It should also be noted that just like the paper, there is an air core in the middle section of our geometry. And in this slide, you can see the velocity distribution in the middle plane of our geometry, and you can compare this contour with the contour presented in the paper. Now, as was mentioned in earlier slides about defining a line in the middle section of the geometry with z value equal to 18 millimeters, we have defined this line. And finally, in this slide, you can see that in this graph, we have compared our CFD simulation results with the results presented in the paper, and you can see that good agreement exists between our results and the papers. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide.
Obtain the mesh file and also the full training movie by purchasing this product.
To benefit from MR-CFD services including simulation, consultation, and training, contact our experts via info@mrcfd.com.